This is the introductory slideshow for Honors Physics Unit 1 Kinematics. We'll start this unit off by defining what motion actually is. We'll identify any variables and terms that are involved in calculating for motion. We'll understand what acceleration is and how it plays a role in motion on a linear flat surface or on an inclined plane. And we'll understand motion from different perspectives or different frames of reference. First, we need to be able to define what motion is. We'll start off with the term kinematics. Kinematics, if you look at the root word kinetic, means movement. And kinematics is a study and the calculation of motion and movement, and without any concern as to what causes this actual motion. So you can think of kinematics as the what of motion. It's I'm traveling at a certain speed. What is the average speed that I'm traveling at? How long did it take me to get there? How far did I travel? So it doesn't tell me how I actually moved or why, just what I actually did. We measure kinematic variables in two ways. The first is called a scalar quantity. A scalar quantity is a quantity that has magnitude only, such as distance, speed, mass, and time. If you say I'm traveling at 5 miles an hour, it doesn't tell me anything except how fast you're going. It doesn't tell me if you're going north or south or at 30 degrees or at 20 degrees. If you tell me I walked for 50 miles, well, you could have gone in a circle around your house for 50 miles, or you could have gone in a straight line. It doesn't tell me anything about direction, just how far you went. Same with mass and time. Something's 10 kilograms, it doesn't tell me any directional value, just how much matter there is. The other way we measure kinematic variables is with vector quantities. Vector quantities have magnitude, but they also have a direction now. A velocity, for instance, is speed with direction. I travel 5 miles an hour north. A displacement is a distance with a direction now. I traveled 5 miles east, or 5 miles at 30 degrees. And acceleration is the rate at which velocity is changing. We'll find that that also has directional values as well. The first quantity we'll start off with is displacement. Displacement is the distance that you travel in a straight line from point A to point B. You often hear the cliche terms as a crow flies, a beeline, a straight shot. As a crow flies is basically the way a bird flies, in a straight line without regards to any obstacles on the ground. A beeline, bees tend to make straight lines back to their hive or to flowers, and a straight shot is, well, it's a straight shot in one straight direction. We represent the displacement variable with a lowercase d, not a capital D, which can be used for density or other variables, and we use the metric unit meters, which is a lowercase m. We're going to use the metric system for pretty much all of our units that we'll be covering in physics, because it's what the majority of the world uses, except us in good old US of A. Another vector quantity that we use, velocity, is the rate at which this displacement is changing over a time interval. You'll see that many of our variables are rates at which other variables are changing. This one, for instance, the rate at which displacement changes. It has a directional value, usually as a degree made with the x-axis. For instance, if I lay out a path on a piece of paper, I can define 30 degrees from the x-axis as the direction I'm traveling. If I was to do this on a map, I would use latitude and longitude. Velocity, a lot of times in this case for Unit 1, we'll be dealing with linear motion, which is motion on a straight line. So I won't be designating direction. So oftentimes you'll hear me call it either velocity or speed. It's interchangeable on a linear system because direction isn't necessarily needed to be stated. But in any case, we'll use the lowercase v as the variable for velocity. We won't use s for speed or r for rate. We'll use lowercase v. Not a capital V, because that could go for volume or other variables, and we'll use the unit, since it's displacement over time and displacement was in meters, we'll use the unit meters per second. The next variable we'll be using is acceleration. Acceleration is the rate at which velocity changes over time. So if you think about it, it's the rate at which the rate of displacement changing is changing, which is kind of confusing. But it's basically, we see it a lot of times in our cars as picking up speed or slowing down. It has a directional value, usually as a degree made with the x-axis, and it also has a positive and negative value to it. A positive acceleration means a direction or a directional change or speeding up, it could be. A negative acceleration can either mean a direction or it could mean slowing down. Most often for our case, since we're dealing with linear acceleration, motion on a linear flat line, we'll be dealing with speeding up and slowing down, and that positive and negative value will play a big role in our calculations later on. We'll use the variable as a lowercase a, and since it's velocity per second, velocity is in meters per second, and that meters per second will be per second, which once you take the, here, let me draw it out, meters per second, as you can see with the division, that meters per second, this second and this second cancel out to form this square, so you end up with meters per second squared. Let me get rid of that so you can see it. Okay. Now that we've identified the variables that we're going to be using in kinematics, we can now start to look at the equations that we can be using, which are basically representations of how these variables interact with each other, how distance can change or time can change at certain velocities or certain acceleration rates. They're used basically for describing motion of an object, and for our case it will be for a single dimension. We're going to look at equations that have dependence or independence of time. Believe it or not, you can actually calculate how fast something is traveling without the use of time. We're also going to use these equations to solve problems for objects that are moving at constant accelerations on straight lines or constant velocities on straight lines. We'll be using these equations quite a bit in the next couple of units, so make sure you're comfortable with them. And as a good rule of thumb, it would be a good idea to get a blank sheet of paper. I wrote blank here, right there, my bad. Blank sheet of paper, preferably in the front of your notebook, to do a list of equations that we develop for each unit. Try to keep them bundled per unit. This will become handy during test time and especially during the final. I'll allow you to use your list during the final as long as it does not have anything else in it. This is so that you can easily reference any of the formulas that we're going to be using throughout this course. Okay, so here we go. Our first kinematics equation. It's a very basic one, average velocity. Velocity is the rate at which displacement changes over a time interval, and it can be written as V_av equals d over t. The av here equals average. We use a lot of subscripts in this unit, especially, well, in this subject, in physics, to express different things. A lot of times you'll be using multiple different variables, and the only way to distinguish between the same variable that's being used in different ways is to use subscripts. So we use them a lot. So whenever you see a subscript, it's not actually variables that you multiply by, it's a descriptor. So in this case, we can take the definition of velocity and translate it into an equation with velocity equals distance over time, a rate of displacement over a time interval. We can rearrange this, and it's preferable for us to rearrange it into d equals v_av t, and a lot of times I'll just say v. So d equals vt. This is going to be preferential to us later on when we start to calculate some more advanced equations, and we're going to take a look at how this average velocity is used coming up in some of the time-dependent and time-independent equations. Average velocity can also be written quite simply as an average. When you average something, you add up all of the things that you're averaging and divide by the number of things that you have. We need to establish some descriptive subscripts for this. So we have here VI, where the I stands for initial, meaning a starting velocity. In some physics textbooks you'll see it written as VO, which the O equals the not variable. The not variable is kind of a basic standard that a lot of the more advanced physics books use for indicating an initial starting point. So our book uses I for initial, and I use I mostly for this course. So we're going to use VI as our initial velocity. The F is going to be our final velocity, and a lot of times we're just going to use two velocities, a starting velocity and an ending velocity, to keep things simpler. If you think about it, everything really has a starting and an ending, and if there's multiple velocities you travel during a trip, it's really a starting and an ending before you start and end a new set, and then another set, and then another set. So we really only need these two variables. Make sure you keep that a lowercase I and a lowercase f though. The equation we can simply write for average velocity is the sum of two velocities, a final and an initial, And since there's two of them, we divide by 2 to get an average. This is a pretty straightforward, easy formula that we use. You use this formula a lot when you're trying to average your test scores or homework scores or things like that. It's the same idea. But we're going to be using this in order to make up some more advanced formulas in the future. So it may seem elementary, but it's actually very important. Our second equation is the one for acceleration, the rate at which velocity is changing. Now the delta right here, if you remember from some previous math classes, delta means a change. So delta v means a change in velocity, the difference between two velocities. Now to do this, we're going to do vf minus vi as our change. The reason we do our final velocity first is because that's going to help establish a positive and a negative. If you think about it, I'm going from 0 to 60 miles an hour. If I take that 0 and subtract 60, I now have a negative number, which isn't something that I want in terms of an idea of speeding up. Speeding up's not usually a negative, it's a positive. So I do the 60 minus the 0 to get a positive value, which indicates a positive acceleration. So it's important to keep in mind that the VF comes first minus the VI. So let's say I went from 40 miles an hour to 60 miles an hour. That's a positive increase of 20. 60 minus 40 is positive 20. So keep that in mind. This is your second equation to be writing down. A equals delta V over T. We're going to see it spread out a little later on. And this is the little later on. If you substitute the Vf minus Vi for the delta V in the equation, your acceleration becomes A equals Vf minus Vi over T. This is going to be an important formula later on when we're dealing with other units such as free fall, projectile motion, Newton's laws of forces, things like that. So make sure you understand this formula as a difference in velocities over a time interval. So if I'm going from 40 miles an hour to 60 miles an hour and it takes me 2 seconds, we hear this one all the time. I bought a brand new sports car. It can go from 0 to 60 miles an hour in 4.5 seconds. Well, that's an acceleration rate we're talking about, and that's your Vf minus Vi over T. So keep this one handy. Okay, we've got the basic equations down now, the simple ones. We're now going to look at the time-dependent and time-independent motion equations. These ones, if you think back to that original formula, d equals vt, that one really sums it up. If you think about it, an entire trip that you could travel could be summed up as a total distance you traveled over a total time to get an average velocity you could have done. Regardless of all the ups and downs you had, you can average everything. So what we want is we want to get an equation that has all of the variables in it, the VFs, the VIs, the acceleration rates, everything that you could possibly have in these equations we want into some kind of master equations. These equations are going to be used to calculate objects' motions with or without the use of time, but first, in order to get these, we have to derive them, which we all love from math class, and it takes me a little while to explain, so make sure you keep up. Keep up. Okay, the first one is the time-dependent motion formula, which means you actually have to know how long something's been traveling for. A lot of times in lab we'll use stopwatches or these photographic gate systems that kind of act like stopwatches. You encounter them when you cross a doorway going into a store and you hear a bell go off. That's basically what's called a photo gate. So we need equations that deal with time, but we also want to get past this idea of an average velocity, and we want to get acceleration in there. In order to do that, we're going to have to substitute some variables. So the first one we're going to look at is that formula VAV equals VF plus VI over 2. That formula from earlier. We're going to substitute that in right here where that VAV was. That will get us an initial and a final velocity built into the equation of that original average velocity for displacement. That will allow us then to get some other variables into the equation. So let's see where that brings us. In order to get acceleration into the equation, I have to take that original formula A equals VF minus VI over T, and I've got to rearrange it. What I'm going to do is I'm going to multiply that time over, and then I'm going to add that VI so that I end up with this equation, VF equals VI plus AT. Now what that's going to do is allow me to take this half, this VI plus AT, and substitute it into that equation earlier where the final velocity was. So now I've taken final velocity and I've changed it. And if you think about that part of it, final velocity is really what you started with plus the rate at which you changed and how long you changed for and what you ended up at. So you're looking at what you started with plus the rate at which you changed your velocity and how long you changed it for to get a final velocity. That we can substitute in there. Now, quite simply enough, we have all our variables in there. Now all we need to do is simplify. So what I'm going to do is I'm going to take that divided by 2 from that average out, and I'm going to bring it up front here. I'm going to take it out of everything and I'm going to bring it up front. Let's see if I can get rid of that. I can erase this. I just kind of want to get it out of your way. So I'm going to bring that 1/2 up front, and that allows me to get it out of the variable lineup. I'm then going to take that time variable that you see right here, and I'm going to distribute it throughout all of this. So by taking time and multiplying by time, I get time squared, and then by taking time multiplying by 2vi, I get 2vi times t. Okay, and that's going to get that time variable cleaned up. And once I multiply the 1/2 by the 2vit and the at squared, it's going to cancel out the 2 here, and it's going to multiply over here. So what I end up with is d equals vit plus 1/2 at squared. And that is my time-dependent motion formula. This is going to become very important later on when we get into free fall and projectile motion, where we have to deal with average velocities that don't change and velocities that do change, all in one problem. So this formula is going to be very important in the future for us. Okay, now for the time-independent motion formula. This is the formula that we can use if we don't have a stopwatch, for example, but we're in our car. Let's say our clock is broken. This is the formula that we can use if we don't want to find time variables, or if we want to get time variables out of there, or if we're dealing with initial and final velocities. So it's also a very important formula that we can use. Now the same idea, I'm going to use that VAV equals VF plus VI over 2 formula, and I'm going to substitute that in for the VAV. So again, I get my final and initial velocities in there. But now I've got to work on that time variable. Since this equation is time independent, I want to get time out of the equation. So I'm going to use this A equals VF minus VI over T formula again, and I'm going to multiply the time over to this side and divide both sides by acceleration. So I end up with time equals velocity, final velocity minus initial velocity divided by acceleration. And what that does is it isolates the time variable. I'm then going to take that and I'm going to plug it into this equation, so I get d equals VF plus VI over 2, that was my average velocity, times VF minus VI over A, that was my time variable. And it looks a little messy. We've got final and initial velocities everywhere and things we have to clean up. But now that we do have all of our variables there, we can start to simplify this formula. I'm going to first multiply both sides by 2 and both sides by A at the same time to get, over here with the D, to get the final and initial velocity setups over there equal to 2 times A times D. I'm then going to use a property of math, which you'll see as the difference of 2 squares, if you remember that one. And I'm going to take that VF plus VI times VF minus VI and reduce it to VF squared minus VI squared. VF squared minus VI squared equals 2AD. That is my time-independent motion formula. And if you see there's no time variable in there, it's very cleanly set up. Now if you want to look at this one, it's actually kind of interesting. If you look at the units, For velocity, you have meters per second, and since over here it's squared, that actually equals meters squared over seconds squared. If you look over here, acceleration is meters per second squared, and I'm multiplying by distance, which is meters, which gives me meters squared over seconds squared. So the units work out on both sides with my meters squared per second squared, and meters squared per second squared. So the formula does work, and all these variables that we have do cancel each other out. And it's nice to have two formulas now that one deals with final velocity, the other deals with time. So here's a list of all the equations that we have so far. Please write these equations down in that blank sheet of paper that you have that hopefully starts out your notebook. We have some very simple ones, from average velocity formulas to a very simple acceleration formula to our two main time-dependent displacement formulas and time-independent displacement formulas. Make sure you copy these down and put them in some convenient areas so that you use these. You'll be using them for the next couple of units. Pretty much every unit in physics we're going to use these formulas for. So this is the end of the Unit 1 introductory video. On the website there is a file, a PDF file called Unit 1 Intro Printable. You can print that and use it to follow along with this video anytime you would like.